Hello, today we're going to start by solving a problem. What is the maximum range you can throw an object if it is thrown within a velocity of 30 meters per second at a 45-degree angle from an elevated initial height of 10 meters? Let's start with writing down the things that we know about the problem. And since we know things in multiple directions, we're going to break it down into the x and y directions. So in the x direction, we know that the acceleration in the x direction is 0 meters per second squared. That is constant. Other than that, we don't know the x velocity. We don't know the distance it travels in the x direction or the range. And we don't know the time it takes to travel this range. A lot of unknowns in the x direction. Let's look at the y direction. Well, we know that its initial starting position is 10 meters above the ground. We also know that everything in the y direction is under the influence of gravity, so it has an acceleration of negative 9.8 meters per second squared. What we don't know its initial y velocity. We don't know the final y velocity. We don't know how high it goes, its maximum height, or the time. But even though we don't know the maximum height, we do know something about it. We know where it lands. We know that its final position is in fact 0. It's the ground level. Okay, so we've just come up with what we know about the problem. Let's get a better idea by graphing what is happening to this problem. Like I said before, we know we're throwing this object, but we know since there is no unbalanced force acting on it in the x direction, that it is not accelerating. So we know the acceleration in the x direction is 0. Well, if the acceleration in the x direction is 0, that means the velocity can't change. But I'm still throwing it in the forward direction, so it must be moving at a constant velocity. Position in the x direction, well, if it's going at a constant velocity forward, that means it must be moving forward at a constant rate. So this is our x direction, position, velocity, and acceleration versus time. Well, what about our y direction? Well, this is a little bit different because we know anything in the y direction is going to be under the influence of gravity. That means it's going to accelerate at negative 9.8 meters per second squared. Well, because it's accelerating downward, we know its velocity has to increase in the downward direction. Well, since we're going to throw it upwards at a 45-degree angle, we know it's going to start at some positive value because it's moving up, but then it's going to slow down and at some point reach 0. That 0 is our max height. And then it's going to go back down, so its velocity is going to be negative. So what does it look like in our position versus time? Well, it doesn't start at 0, it starts at 10. It's going to go up, and then it's going to come down. Just by looking at this, guys, I can tell that this is linear. This is definitely not linear. This looks like a parabola. Tells us this is going to be a quadratic function. Okay? So, what does it actually want in this problem? Well, it wants to know how far is it going to go. That's in our x direction. In fact, that is right here. That is our delta x. Okay, so how are we going to solve this? Well, going back to our graphs, I can see right here that our delta x is a linear graph. So it's got to follow a linear function. So what linear function is it going to follow? Well, let's go through that. I know, since y equals mx plus b, I know that the the y direction is measuring its position, so this is the final position. I know m is the slope, which represents the velocity in the x direction. I know x is the time variable, and OB is the initial position. I know that the initial position is 0, because initial position, 0 is a very good place to start. So I can eliminate that. I want to find out how far it goes. So this is telling me the two things I need right here. I know to find out how far it travels, I need both the velocity in the x direction and the time in the air. These are the two things I need. Well, do I have any of them already? Well, one of them we can find right away. I know that it's being thrown back at my initial position. I know that I was given this information that it was thrown at 30 meters per second, but at a 45-degree angle. Now that doesn't give me any information in my x or y direction immediately, but it will if I break it down into its components. So I know that this is 30 meters per second, but I know that this is made up of two pieces. An x piece, which represents the x velocity, and a y piece, which represents the y velocity, the initial y velocity. I know that I've thrown it at an angle of 45 degrees, so I am actually able to break this up. I can find out what the pieces are, okay? We know our trig functions, we're pretty comfortable with this, and we know that we can find the adjacent side by using a cosine. So, people talk about SOHCAHTOA, this is CAH, the cosine of theta is equal to the adjacent over the hypotenuse. So in this case, our adjacent is our x velocity, and our hypotenuse is our total velocity, which is 30 meters per second. So if I want to solve for Vx, which is our adjacent, I just need to multiply both sides by the hypotenuse. This brings us to 30 times cosine 45 equals my Vx. Okay, and I can solve for that. Once I grab my calculator, which I set way over here. So cosine 45 times 30, this is going to give us 21.21. So I know that my Vx is 21.21 meters per second. Now this, at first glance, seems like it could be correct. Why? Well, the hypotenuse is always the longest side. The adjacent and the opposite side must be smaller than that, and 21.2 is definitely smaller than 30. Because it's a 45-degree angle, I also know that the opposite and adjacent sides are going to be the same. So I actually don't even need to do this side. I do know that they are going to be exactly the same. Well, this is great. Now I know some additional information here. I now know that my x velocity is now 21.2 meters per second, and my initial y velocity is the same, 21.2 meters per second. This takes us another step closer to solving the problem. Let's go back over here, guys. I know I need two things to find out my total distance. I need total distance is equal to my x velocity times time. And now I know my x velocity is 21.2. Now I just need my time. What is going to determine the time? Well, going back here, you guys, I can see that my time stops when the object hits the ground. All these times indicate when the object hits the ground, when the object hits the ground. So when the object hits the ground, my time stops. Well, what determines when it hits the ground? Well, gravity determines when it's going to hit the ground. Gravity, its initial velocity, all these things are going to determine when it hits the ground. And our position function is an excellent way to find out when that time is. I can look at this graph right here and I can see that this is a quadratic function. So we are going to use that to help us solve for the time. So let's bring up this board right here. And let's do this solving, shall we? So what does a quadratic function look like? Well, we know that it's y equals ax squared plus bx plus c. Well, our y-axis is the position, so I know this is the final y position. And I know that the x is time. So that leaves us with three coefficients, a, b, and c. Now we've been in physics for a while, so by this point we know that each one of them determines something very specific about this graph, okay? The a value is the acceleration. In fact, it's 1/2 the acceleration of our object. The b value is the slope of this at any moment in time. So it's the velocity, you guys. It's the velocity in the y direction times time. And the c value is the initial y position. Now we can solve for this, you guys. I know that it ends at 0, and I know the y acceleration is negative 9.8, so half of that is negative 4.9 t squared. I now know my initial y velocity. It's 21.2. So this is 21.2 times time, and I know my initial position is 10. This is now being placed in a very familiar format. We now have a, b, and c coefficients. By this point, we're all very familiar with the quadratic formula. The quadratic formula provides a very, very good way to find out what our t variable, in this case, x variable here, is in a quadratic, you guys. So I know that t is going to be equal to negative b, negative b plus or minus the square root of b squared minus 4ac all over 2a. So now it's just a matter of putting in our coefficients. Negative 21.2 plus or minus the square root of 21.2 squared minus 4 times negative 4.9 times 10 all over twice a, which is going to be negative 9.8, you guys. So why is there a plus and a minus? That means there's going to be two solutions. There's two moments in time when this object hits the ground, okay? So that's true. If you take a look at this quadratic graph we have, we know that when it's launched, at some moment in time t, it's going to reach the ground here. Now what a lot of people forget is that if we look at this graph, a parabola is symmetrical. That we know on the left side of this, this could have reached the ground at some moment before the object was thrown, if we project it out. If it was thrown at the ground, this would have followed the same path. So this is going to give us a value of negative time. Well, we know that negative time is not valid here because we need the forward position. We need to know when that is. So we need to look for the forward answer. That helps us realize which one we're going to use. We now know that we're going to use the negative. Why? Because we have a negative up top, a negative at bottom. If we have a positive up here, that is going to make this into a positive number, giving us negative time. So I know that I'm going to use a negative time here. So, doing a little solving, 10 times negative 4.9 times negative 4 plus 21.2 squared, square root of that, minus negative 21.2 divided by negative 9.8. It gives us a time of 4.75 seconds. So now we have a time. we have a time. That's very important. So I can put that in here. So what is that? That's when it hits the ground. So I know this is 4.75 seconds. But here's something interesting, guys. This is not only the point when it hits the ground, this is also the point where it stops moving forward. So it's the time in both the x and y direction. 4.75 seconds. Now we can finally solve the problem. Going back to our original realization, we realized that to solve this problem, we need to multiply its x velocity times its time. Now we finally have its time. So, I know that its final x position is simply going to be this x velocity, 21.2, times this time that we figured out with our quadratic. 4.75 seconds. So when we put those together, we get about 100.8 meters. So I know that this object is going to land 100.8 meters. Another way to confirm this, you guys, once again, we always go back to the graphs. We know something very interesting about these graphs. The area under our velocity versus time graph, you guys, will give us our change in position. So the area under our Vx versus time will give us our change in position. So this is essentially what we just did here. We know our velocity was 21.2. We know our time is 4.75. The area under here is certainly going to be the same, 100.8 meters. So that confirms it. So thank you for solving this problem with me. Have a good day.